Hi students, hope you all are well. Welcome to the online lecture series of digital communication, and we are starting unit number 3, random signal and noise. So before proceeding to our today's lecture, let's have a quick revision that what we have studied in our previous lecture. In our previous lecture, we have seen ensemble averages and time averages. So what were ensemble averages and time averages? The expectations or ensemble averages of a stochastic process that is also called as random process x of t are averages across the process at a particular instant of time. Then we have seen the mean function and the autocorrelation function of ensemble averages. After that, we have seen time averages. The long-term sample averages or time averages are that averages which are along the process. After that, we have seen ergodic process. That what is ergodic process? So sample process is called ergodic process if time averages are equal to ensemble averages. Then we have seen the ergodicity in mean, and we have seen the two conditions in that. So what were the two conditions? The first condition, it states that time mean it approaches ensemble mean as the observation interval t, it approaches what? Infinity. And the second condition we have seen that variance of time mean is 0 when the observational time t, it approaches what? Infinity. After that, we have seen ergodicity in autocorrelation. In that also we have satisfied the two conditions. What were the two conditions? The first condition, it says that time average autocorrelation function, it approaches ensemble autocorrelation as observational interval t, it approaches infinity. And in the same we have seen the second condition, it was that the variance of time average autocorrelation is 0 as observational time t, it approaches what? Infinity. After that, we have studied the transmission of random process through LTI filter. In that, we have mathematically seen that mean and autocorrelation function, they also depends on what? Time shift. So if the input to a stable linear time invariant filter, it is a wide sense stationary random process, then the output of the filter is also what? Wide sense stationary random process. So today we are going to see the topics power spectral densities of a random process and properties of random process. So moving towards our today's topic, that is power spectral density. In our last lecture, we have seen the characterization of wide sense stationary random process in linear system in the time domain. If you remember, while studying the transmission of random process through LTI filter, we have derived the relation for autocorrelation function. That would be in what? Time domain relationship. Now today we are going to study the power spectral density. So this is also one of the characteristic of your wide sense stationary process, which we are going to see using what? Frequency domain relationship. Now we know the autocorrelation function of an output process y of t, it is given by r of y tau is equal to expectation of y of t plus tau. So make it as equation number 1. In our previous lecture, if you remember, the another definition of autocorrelation function that we derived, it was what? R of y tau is equal to double integration from minus infinity to plus infinity h of tau 1, h of tau 2, Rx tau plus tau 2 minus tau 1 d tau 1 d tau 2. So make it as equation number 2. So along with me, you also write the equation so that you would understand this lecture. Now, for tau equal to 0, if we are going to put tau equal to 0, then equation 1 and equation 2, it would become what? That expectation of y of t plus 0. That would be what? Expectation of y square of t. So it is a mean square value of your random process, which is nothing but your double integration from minus infinity to infinity h of tau 1, h of tau 2, Rx, since tau equal to 0, so it would be just become tau 2 minus tau 1 d tau 1 d tau 2. So make it that's equation number 3. As we know, the impulse response h of tau 1 or h of tau 2, it has a Fourier transform of what? H of f, which is nothing but the frequency response of your linear time invariant filter. The impulse response of linear time invariant filter is equal to the inverse Fourier transform of the transfer function of the system, so that we would get h of tau 1 is equal to integration from minus infinity to plus infinity h of f e raised to j 2 pi f tau 1 df. Make it as equation number 4. H of f is nothing but your what? Frequency response of your LTI filter. Now, if we will put this equation number 4 in equation number 3, then what we would get it? That expectation of y square of t, that is mean square value of random process, is equal to what? Double integration from minus infinity to infinity, and putting the value of h of tau 1 equation number 3, it would become what? Integration from minus infinity to infinity h of f e raised to j 2 pi f tau 1 df, and the rest remaining field it would be same, that is h of tau 2 Rx tau 2 minus tau 1 the d tau 1 d tau 2. Now by rearranging this integration, what we would get? Integration from minus infinity to infinity h of f df. This is would be the first part. Second part, it is a integration from minus infinity to infinity h of tau 2 d tau 2, it is a second field, second integral, and third integral it would be minus infinity to infinity Rx tau 2 minus tau 1 e raised to j 2 pi f tau 1 d tau 1. Now we would define a new variable, say tau. This tau is equal to what? Tau 2 minus tau 1. So tau is equal to tau 2 minus tau 1, or we can write tau 1 is equal to what? Tau 2 plus tau tau 2 minus tau, and hence d tau 1 is equal to what? Minus d tau. Now, so we can put the value of this tau here. So this equation, it would become mean square value of this random process is equal to integration from minus infinity to infinity h of f df, integration from minus infinity to infinity h of tau 2 d tau 2. Over here, integration from minus infinity to infinity Rx tau. Why? Because we have put tau 2 minus tau 1 is equal to what? Tau. So this tau 1, it would be equal to what? Tau 2 minus tau 2. So you have to put tau 1 equal to what? Tau 2 minus tau 2. So we can separate out this, that e raised to j 2 pi f tau 2 e raised to minus j 2 pi f tau 1 d tau. Now guys, I have skipped one step over here. As we know that d tau 1 is equal to what? Minus d tau. So if it is going to become a minus d tau, then the integration it is going to change from infinity to minus infinity. But if you want to again make it as a minus infinity to infinity, then this minus d tau it would become positive. So after this step it would come, and you can write it that it is what d tau, and integration it is from minus infinity to infinity. The previous step that I told, if you want to write it over here minus d tau, then the integration limits would be changed. It would change from infinity to minus infinity. But again, what we are going to do it, we are going to make it as minus infinity to infinity, then that minus d tau become positive. So that's why I have written directly this step. Now, by rearranging this one, what we are going to do it, integration from minus infinity to infinity h of f df. Now see, integration from minus infinity to infinity h of tau 2, and this part we have taken over here, it would become e raised to j2 pi f tau 2 d tau 2, and what remain then, integration from minus infinity to infinity rx tau e raised to minus j2 pi f tau 1 d tau. Now this term, focus on this term, that is integration from minus infinity to infinity h of tau 2 e raised to j2 pi f tau 2 d tau 2. It is nothing but complex conjugate of the Fourier transform, that is h convolved with f. So the previous equation it would become what? Mean square value of your output process is equal to minus infinity to infinity h of f, and that second integral, which is nothing but your complex conjugate. So we have written this h convolution of f, that is a complex conjugate h of f df. Third integral would remain same, minus infinity to infinity rx tau e raised to minus j2 pi f tau d tau. So this above equation would become integration from minus infinity to infinity mod of h of f square df, writing the same term as it is. Now this is nothing but the Fourier transform of your autocorrelation function rx tau. This term it is what? Fourier transform of your autocorrelation function rx tau. So make it as equation number 5th. So the Fourier transform of Rx tau is called what? Power spectral density, which is denoted by what? S of x of f. So we can write this term, that is S of x of f is equal to integration from minus infinity to infinity Rx tau e raised to minus j2 pi f tau d tau. Make it as equation number 6. Now putting equation number 6 in equation number 5. So what you would get, the final equation, that expectation of y square of t, that is mean square value of your random process, is equal to minus infinity to infinity hf square. This term is nothing but your Sxf. So we have written Sxf, which is nothing but your power spectral density df. So make it as equation number 7. So equation number 7, it states that mean square value of the output, mean square value of this output y of t of a stable linear time invariant filter in response to a wide sense stationary process is equal to the what? Integral over all the frequencies of the power spectral density of the input random process, which is multiplied by with squared magnitude of the transfer function of the filter. So we have seen the characterization of this wide sense stationary random process in frequency domain relationship. So after getting this power spectral density, now we will see the properties of your power spectral density. So the next topic of our today's lecture, it is what? Properties of the power spectral density. Now, as we know, the power spectral density xxf and the autocorrelation function Rx tau of a wide sense stationary random process x of t, they form a Fourier transform pair. That is what? S subscript x of f is equal to integration from minus infinity to plus infinity Rx tau e raised to minus j2 pi f tau d tau. Make it as equation number 1. While looking all the properties, there are 5 properties of your power spectral density. For that we are going to use this equation. So please write this equation so you can understand it easily. And second is the autocorrelation function, that is Rx tau. Now that Rx tau is equal to integration from minus infinity to plus infinity Sx f e raised to j2 pi f tau df, and make it as equation number 2. Now these two equations are called Einstein-Wiener-Khinchin relations. What? Einstein-Wiener-Khinchin's relation. So first property 1 of your PSD, it is going to tell you, it states that the zero frequency value of the power spectral density of your wide sense stationary random process is equal to the what? Total area under the autocorrelation function, right? So from equation 1, this is the equation number 1. If I am going to put what? F equal to 0, the zero frequency value. So if I am going to put F over equal to 0, then the equation, it would become what? Ss x of 0 is equal to integration from minus infinity to plus infinity Rx tau e raised to 0, because f is equal to 0. So it would become what? E raised to 0 d tau. So as we know that e raised to 0 is nothing but your 1. So this equation, it would become Sx of 0 is equal to integration from minus infinity to infinity Rx tau d tau. Moving towards the second property of PSD, it states that the mean square value of a wide sense stationary random process is equals the what? Total area under this graph of power spectral density curve. So we can write it as expectation of x square of t is equal to integration from, that is equals a total area. So integration from minus infinity to infinity Sxx f df, because it is what? Power spectral density. So make it as equation number 3, because we are going to use this equation. So just remember this equation. Now we would prove it, that how this equation it comes. Now we know that Rx tau is equal to what? Expectation of x of t plus tau. So with tau equal to 0, if you put tau equal to 0, what you would get? Rx 0, expectation of x of t plus tau, but tau equal to 0, so it would become what? X of t. So which is nothing but of square of this x square t. So it would become expectation of x square t, which is equal to Rx 0. And we know that Rx 0, it is equal to integration from minus infinity to infinity and Sxf e raised to 0 df. That is from equation number 2. We have put this term, since tau over here equal to 0, so we put e raised to 0, and as we know e raised to 0 is 1. So this mean square value of your wide sense stationary random process, it is going to become equal to the what? Total area, that is integration from minus infinity to infinity under these power spectral density curve, and hence we prove that E of x square t is equal to integral from minus infinity to infinity Sxf df. Now moving towards the third property. The third property, it states that the power spectral density of a wide sense stationary random process is always what? Non-negative, or we can say it is always positive. So that's why we have written the PSD, that is Sx of f, it always greater than or equal to 0 for all values of your f frequency. So just while deriving the equation for your power spectral density, we have derived this equation that E of y square of t is equal to integration from minus infinity to infinity square of this transfer function Sx f df. So over here, since it is a square term, it is always what? Positive. And this is a squared magnitude response of your transfer function hf square, so which is also positive. Hence the PSD, that is a power spectral density, it will also be what? Positive. Now moving towards the property number 4. The property 4th, it is going to tell you that the power spectral density of a real valued random process is an even function of frequency, that is Sx minus f is equal to Sx f. So now we will see that how we are going to prove this. Now from equation number 1, we have seen that Sxf, that is a power spectral density Sxf is equal to what? Integration from minus infinity to infinity Rx tau e raised to minus j2 pi f tau d tau. So replacing this frequency f by minus f. So what it would become? It would become Sx minus f integration from minus infinity to infinity Rx tau e raised to j2 pi minus f tau. So minus minus become what? Positive, and it is e raised to j2 pi f tau d tau. Now replacing tau by minus tau. So you have to put what? Minus tau in our previous equation. So it would become what? Sx minus f is equal to integration from minus, that is plus infinity to minus infinity. Why is it so? Because d tau, it become what? Minus d tau. So the limits, it is going to change from plus infinity to minus infinity. Rx minus tau e raised to tau is what? Minus tau, so it would become e raised to minus j2 pi f tau, and this d tau would become minus d tau. Now to make this minus d tau positive, what we have to do it? We have to interchange the limits, that is this limit, it is going to change now from, it would be what? Minus infinity to infinity, so that this minus d tau become positive, it would be d tau, and Rx minus tau e raised to minus j2 pi f tau. As we know, this Rx minus tau is equal to Rx tau, which is not what? Even function. So putting the value of Rx, that is minus tau, is equal to plus tau. So put it this Rx tau in this equation. So you would get Sx minus f is equal to what? Integration from minus infinity to infinity Rx tau e raised to minus j2 pi f tau d tau. And as we know, this is your Sxf, that is from equation number 1. It is your power spectral density. So we can say that the power spectral density of a real valued random process is what? Even function, that is Sx minus f is equal to Sxf. Now the last property is property number 5th. It states that the power spectral density appropriately normalized, it has the properties usually associated with a what? probability density function. So let us define the normalized PSD by what? Small px of f, which is given as pxf is equal to sxf divided by integration from minus infinity to infinity sxf df. So thus this sxf is what? Normalized with respect to the total area under its graph. So as we have seen in property number 2 and 3, so we note that pxf is always greater than or equal to 0 for all values of frequency. And the total area under pxf is unity. So we can write it as integration from pxf df is equal to integration sxf df upon integration from minus infinity to infinity sxf df is always equal to 1. So hence these two aspects, it shows that normal power spectral density, it behaves like what? Your probability density function. So the summary of our today's lecture, we have studied the power spectral density, and in that we have seen that mean square value of the output of a stable linear time invariant filter in response to a wide sense stationary process is equal to what? The integral over all the frequencies of power spectral density of the input random process, which is multiplied by what? Squared magnitude of the transfer function of the filter. After that, we have studied the properties of power spectral density. In this, we have studied the 5 properties of power spectral density. We have seen 2 equations, that is, first is PSD equation, power spectral density equation, which is denoted by Sxf, which is integration from minus infinity to infinity, Rx tau e raised to minus j 2 pi f tau d tau, and we make it as equation number 1. And second, we have seen the autocorrelation function, that is Rx tau, which was what? Integration from minus infinity to infinity Sxf e raised to j 2 pi f tau df, and which we make it as, mark it as equation number 2. So these two equations are called what? Einstein-Wiener-Khinchin relationships. So based on these two equations, we have seen the 5 properties of your power spectral density. After that, this is the assignment. So please note down this assignment, as you have to submit this assignment. So while explaining the power spectral density, you have to mathematically, you have to prove it, that we have seen in the lecture. And also while defining the properties, you have to state each property and then you have to prove it by using what? Einstein-Wiener-Khinchin relations. In next lecture, we are going to see that what is Gaussian process and what is noise, what are the different sources of noise that is there. So if you have any question or any query, you can post it onto my email, which is seen on your screen. So it's all about today's lecture. Thank you very much. We will meet in next lecture.